Hi everyone, and welcome to this my video on the derivatives of inverse circular functions. My name's Darren from Maths Guru, but you probably already knew that. I mean, it's literally everywhere all over my slides. Thanks very much for joining me for this, a video in the Specialist Maths course. It doesn't matter if you don't know what Specialist Maths is. Basically, it is there all around the world to be able to find the derivatives of inverse circular functions. Let's get started. Now, in the previous video, if you haven't already watched it, it is amazing. We looked at the idea of what would happen if we had functions in the form of x as some sort of function of y. And more importantly, if we had it that way, what could we do to differentiate it? Now, there were some pretty contrived examples in that video, and I said to you it would have a greater purpose. And actually, as it turns out, today is that greater purpose because let's look at how we could find the derivatives of sine to the minus 1 of x. Now, we've already met this previously. We've looked at what the graph of the sine to the minus 1 of x actually looks like. And because I love graphs, there is a graph. And I say over and over again, everything you do in methods or specialist maths, really sketch the graph. Because once you see it, you may see through any tricks that the question through all of those words may be trying to sort of lead you down or trip you over with. Right, so let's have a look and see whether we can find the derivative of sine to the minus 1 of x. Ultimately, for those of you who want to know, it's there, basically, all right? And thankfully, it is on the summary sheet for VCE. So you're going to turn around and say, well, why do you want me to do this? Well, actually, the exercise in itself, or the ability to be able to do this, is actually quite interesting. So let's give it a go. Right, well, at the moment, we've got something like y is equal to the sine to the minus 1 of x. No idea how to actually differentiate that at the moment. But what I could do is actually do what? Well, what about if I had the sine of y is equal to x? Yes, what about if I take the sine of both sides? Well, the sine, so if you remember that the sine of the sine to the minus 1 of x would just be x. That sort of makes sense. If you're going to inverse sine and then sine it, you're going to get back to what you actually started with. Well, if we actually now write this as x equals the sine of y, then I can use the information I've had previously to say, well, okay, then the dx by dy, I know what the sine of y is going to become because it just becomes the cosine of y. I don't want dx by dy, I want dy by dx then becomes equal to 1 on the cosine of y. Yeah, no, got a problem. Why have we got a problem? Well, I don't want it in terms of y because normally we want it in terms of x. Cosine of y. Hold on a moment. I know that sine squared of y plus the cosine squared of y is 1. That's that, I don't know, Pythagorean identity that comes over up all the time. So let's say we've got cosine squared of y is 1 minus sine squared of y. Then we could say that the cosine of y is equal to the square root of 1 minus the sine squared of y. Plus or minus? Plus or minus, all right? But in this situation, we're probably only going to be looking for the positives, so let's have it there. Okay, cool. So I can now say, well, that now becomes 1 over the square root of 1 minus sine squared. Oh, hold on, that hasn't actually helped because all I've done is written it in a different way of y. But actually, it has helped because we know from here that if x is equal to the sine of y, then the sine of y equals x. If we square the sine of y, we get sine squared, so we get x squared. So I can now therefore write that as 1 on the square root of 1 minus x squared, and the world goes crazy. Why does it go crazy? Well, because I've just shown how to get that formula. The important thing to notice here, though, is our restriction that x only falls into minus 1 to 1. Why? Because, again, if I draw this graph, what do we notice? Well, sine to the minus 1 of x is only defined between the values of minus 1 and 1. So we have to make sure we understand those restrictions because it may come in handy here. All right, so there we go. So that's formula number 1. What about formula number 2? Could we use the same idea here? So what have we got here? We've got y is equal to the cosine to the minus 1 of x. Take the cosine of both sides, we get cosine of y is equal to x, or x is equal to the cosine of y. We know that dx by dy is equal to what? Well, sine goes to cos and cos goes to minus the sine of y. So then dy by dx is equal to 1 on the minus sine of y. Well, again, we know that sine squared plus cos squared is equal to 1. All right, so we've got sine squared is equal to 1 minus cos squared y. Okay, so that now becomes 1 on, well, hold on a moment, minus sine of y. Oh, well, let's just write that as the sine of y then is equal to the square root of 1 minus cos squared of y. So that becomes y minus 1 on minus 1 minus cos squared of y. And in the same way as we had previously, cos squared gives me x squared. So I'm going to make that as minus 1 on the square root of 1 minus x squared. And again, we have to be careful once again to realize that our domain is that's only going to be true for x values that fall between minus 1 and 1. All right, so there's two formulas. And again, these are in the VCEA formula sheet. What about this one? Whoo, sheesh, or chi-hoo, as Maui says in Moana 2. Giving away my movie taste now. Right, so what have we got? We got y is equal to tan to the minus 1 of x. All right, so tan of y is equal to x. Let's write that around the other way of tan of y. So dx by dy is equal, tan goes to sec squared of y. So dy by dx is equal to 1 on sec squared y. Well, we know that sec squared is 1 plus tan squared of y. All right, so sec squared is equal to 1 plus tan squared. So in which case we get that as 1 on 1 plus the tan squared of y. And again, much like we did the previously, if we know that tan of y is x, tan squared must be x squared. And so we get 1 on 1 plus x squared. And in this situation, x values are, because we've got a pretty little sketch here, all real values. So having got those three formulas, there they are. And thank you very much to Cambridge for allowing me to use your textbooks. You guys rock. I am so grateful. It's saved me hours and hopefully has provided some great examples to everyone out there watching. If you haven't already subscribed, I would really appreciate it. So very few people watch maths videos. The fact you're watching it is deeply humbling. If you can subscribe and sort of spread the word, that would be greatly appreciated. So there we go. There is our values of what we came up with before. Now, actually, these are slightly different if I look at it, because we're now in a situation where we are generalizing it to sine to the minus 1 of x on a, cos to the minus 1 of x on a, and tan to the minus 1 of x on a. Now, these are generalizations in the sense of previously, when we had our a value of 1, then we ended up with 1 minus x squared, minus 1 on 1 minus x squared, and 1 on 1 plus x squared. But obviously we can, if we had the time, go back and actually look at them in terms of having fractions in there. No way am I going to do that at this moment in time. But there we go. That's sort of the general ones for your x on a. Right, here we go. Let's have a look at some examples. Differentiate each of the following with respect to x. Now, there are two ways of doing this. If we have y is equal to sine to the minus 1 of x on 3, I could go straight to my formula, which basically tells me then that y dashed is equal to, what have we got here? So we're going to use the correct one. I'm going to highlight it so that I don't use the wrong one. And that's going to give me, right, 1 on the square root of a squared, which is 3. So 3 squared, which gives me 9, minus x squared. Yeah, there we go. That's the answer. All right, nice and easy for the sine one. But what do we do here with the cosine to the minus 1 of 4x? That doesn't actually seem to fit any of the values that I've got. Well, this is the one that there are two ways of doing it. I got slightly ahead of myself. So if we've got y, he says writing in, let's write in a different color. I'm going to write in orange. Y is equal to cos to the minus 1 of 4x. That doesn't fit any of the ones I've got at this moment in time. So what if I now let u equals 4x? Then I get y is equal to the cos to the minus 1 of just u. Well, if we now make sure we use the correct one, and again, I'm going to highlight it because I am a stickler for making sure I get this right. Now, in this situation, a is going to be equal to 1. So we're going to have that y dashed is equal to minus 1 on the square root of 1 minus x squared times by, right? So realistically, that should be u. I've made a silly mistake Now that should be u squared, but if we go back to the previous video, I get very nervous with that being fitted in there because that y dashed is y with respect to x. So I'm actually going to change that to, my u value was what, 4x all squared times by the differential of this, so u dash is equal to 4 times by 4. So minus 1 times 4 gives me negative 4 on the square root of 1 minus 16x squared. Okay, so minus 4 over 1 minus 16x squared is in fact the correct answer. Now, I've never done this before and I might go horribly wrong, but what I want to now do is say, well, what about if I had y was equal to the cosine to the minus 1 of x on 1/4? Because believe it or not, x on 1/4 is the same as 4x. So in this situation, my value of a now would be 1/4. So y dash is equal to, again, going straight back to this one here, if I had minus 1 on the square root of a squared, which is 1/4 squared, which is 1/16, minus x squared. All right, so now let's do a bit of manipulation. Minus 1 on the square root of 1 minus 16x squared on 16. All right, now that square root sign really should extend over all of that. I should always draw them better. So that's now going to give me minus 1 on the square root of 1 minus 16x squared all on 4. And lo and behold, when I actually manipulate that, that's going to give me minus 4 on the square root of 1 minus 16x squared. Same answer. Now, again, I had no idea if that was going to work. Mathematically, my mind was telling me it should work. But again, lots of ways of doing it. Taking this out and doing it by the chain rule, that was certainly one way of doing it. I could have got a little bit tricked here by writing that as x squared rather than 4x all squared. Alternatively, writing it in this format here by changing my 4x to x on 1/4, same thing, means I've now got an x and an a that I could have put in there. What about this one here? 10 to the minus 1 of 2x on 3. Again, if I was feeling really brave, I could say that that would therefore be tan to the minus 1 of x on 3 on 2. All right, so x on 3 on 2, that gives me my a values. Let's just do it. All right, so if y is equal to, so y dash becomes equal to, I'm actually going to change back to blue. I don't like that orange color. It's too light. Y dash is equal to, right, so what is tan? A on, so I've got 3 on 2 on a squared, which is 9 on 4 plus x squared, which is just there. All right, so now doing a little bit of manipulation, we got 3 on 2, all divided by 9 plus 4x squared, all on 4. Now, because we got a fraction divided by a fraction, I can do keep, change, flip. So that's now same as 3 on 2, and I'm going to multiply that by 4 on 9 plus 4x squared. 2's going to there 2 times. 3 times 2 is 6 on 9 plus 4x squared. And believe it or not, again, correct answer. Now, again, I quite like that. That sort of worked. Another way of doing it is basically taking... I'm just going to duplicate this page and show a different way of doing it. All right, so I haven't copied that. I'm just going to delete all of this so that we can go back to another way of doing it. Now, the great beauty about maths is there's always lots of different ways of doing it. So going back to this one now with y equals tan to the minus 1 of 2x on 3. Let's now let u equals 2x on 3. So du by dx is going to give me 2/3. And we now know that y is equal to tan to the minus 1 of u. Right, so dy, he says, by du is equal to, now in that situation, tan is going to become equal to a, which is 1 on 1 plus x squared. So then dy by dx is going to give me 1. Oh, that shouldn't be x squared. Oh, come on. That should be u squared. So 1 on 1 plus, u was 2x on 3. All squared. We're going to times that by du by dx, which is 2/3. Yuck. Right. So therefore, what have we got here? So we got that dy by dx is going to be equal to 1 on 1 plus 4x squared on 9 times by 2/3, which is going to give me 1 on 9 plus 4x squared all on 9 times 2/3, which is going to give me 9 on 9 plus 4x squared times 2/3. That's going to go in there 3 times. 2 times 3 is going to give me 6, and I'm not going to finish writing that. Now, I don't know about you, but that seemed to be a little nicer than that. Same answer, but anyway. Right, next one. Differentiate each of the following. Oh, what am I saying? I'm repeating the question. Sine to the minus 1 of x squared minus 1. I don't think I've got any choice here except to be able to take that out. So we've got y is equal to, what have we got? Sine to the minus 1 of x squared minus 1. Let u equals x squared minus 1. Du by dx is going to give me 2x. Okay. So y dy by du is going to give me, sine to the minus 1 of that is going to give me 1 on the square root of 1 minus u squared. Okay. So therefore, dy by dx is going to give me 1 on the square root of 1 minus u squared, which is x squared minus 1, all squared, times by 2x, which is going to give me 2x on. Now, I'm going to shortcut this and not worry about multiplying all that out because I've got the answer in front of me. So I'm going to say that becomes equal to 2x squared minus x to the power of 4 when I do some manipulation. So all I've really done there is I've squared that out and manipulated it to get me to the simplified form. Right, now, in this situation, we seem to have a factor. So I've got that dy by dx becomes equal to 2x on, take out the root of x squared, times by the root of, that gives me, what is that, 2 minus x squared. Now, the reason I am taking that out, because I know that the square root of x squared is mod x. So that now becomes that dy by dx is equal to 2x on the modulus of x times the root of 2 minus x squared. Right, now obviously in this situation, because the modulus of x is there, we've got a plus x and a minus x. We've got to take account of signs in that situation. But more importantly, whenever you've got a question that has a denominator as a fraction, you've got to work out what is, if any, are the restrictions for the domain. And in this situation, remember, we cannot have a square root that is negative. Now, what I therefore know is that when I solve this, I get, and I always tend to draw a graph when I do those things. If I was to draw this graph, I'd end up with something looking like that. This point here, that would be 2. That point there, believe it or not, would be root 2. And that one there would be negative root 2. How? All I did was solve 2 equals x squared. And I got minus root 2 and root 2. Okay, so we now have some values here. So my x values seem to be positive between 0 and root 2. So when my x values are positive, so for my values of 0 is less than or equal to x, which is less than or, I said less than or equal to. 0 is less than x, which is less than root 2. Now, bearing in mind, x cannot be 0. Why can x not be 0? Simply because we're going to have that one there, all right? So the modulus of 0 is 0. That would end up not being anything. If I had root 2 and I put root 2 in here, that would end up being 0. So we'd have all sorts of problems in that situation. So we've got to be very careful about our inequalities and what we use them. So in that situation, x is positive. So therefore, my dy by dx is going to be, well, if this x here is positive, that x is going to cancel just to give me 2 on the square root of 2 minus x squared. For the values of minus root 2 less than, x less than 0. All right, we know that our x values are negative there. My dy by dx is going to be equal to negative 2 on the square root of 2 minus x squared. Again, why is it going to be negative? Because that will be minus x, that will be x, the x and the minus x will cancel to give just the minus, and I just put it on the top. Now again, that was a long example, but it shows how much you've got to think about for specialist maths, particularly when you have fractions. You've got to make sure that you consider the domain of where that fraction is to make sure that you don't have values in there that don't make any sense, and also whatever. Right, Learning objectives revisited. Did we understand how to find and use the derivatives of inverse circular functions? Yes, we built on that previous knowledge. We realized that actually by having things in terms of x equals, some sort of function of y allows us to differentiate so much easier. Hopefully you found that useful. If you have, please subscribe to my YouTube channel and like the video and leave me a comment. And hopefully I'll see you in another one. There's so much more coming. All right, until the next time, take care. Bye-bye.